You've seen the headlines. We reached Pluto. We found planets around Proxima Centauri. And it's easy to think, cool, so we're basically halfway to the stars, right? But the truth is brutal. We are not even close. In this video, we're going to strip away the sci-fi and walk through why a 10-year sprint to Pluto is already a heroic edge case for our rockets, and why doing anything similar to Proxima would demand speeds, power, money, and patience so far beyond what we have that it might as well be another kind of physics. If you've ever wondered, why don't we just go there? This is the video where you find out exactly why just is doing most of the lying. But before we continue, please subscribe to the channel to give your support. Let's continue. You think you understand what far means. You've done long flights, you've seen solar system posters, you've heard numbers like millions of kilometers all your life. But that intuition fails as soon as you look at Pluto. And it completely breaks when you look at Proxima Centauri, the closest star beyond the sun. Your brain is good at meters, at kilometers, maybe at thousands of kilometers. It is not built for billions, and it is definitely not built for trillions. So let's put real numbers on these distances and see why Pluto is barely within reach, and Proxima is not. Start with something familiar, the distance from Earth to the Sun, 1 astronomical unit, 1 AU, about 150 million kilometers, roughly 93 million miles. That is the basic measuring stick of the solar system. Pluto does not sit at 1 AU. It orbits between roughly 30 and 49 AU from the Sun. At the far end, that is around 5.9 billion kilometers, about 3.7 billion miles, roughly 40 times farther out than Earth. So when we talk about the outer solar system, we mean tens of Earth-Sun distances away. Now look at what it takes to actually get there. New Horizons, the Pluto mission, launched on an Atlas V, one of the most powerful rockets in service. It got an extra push from an upper stage and a gravity assist from Jupiter. After all that, the probe was moving at roughly 14 to 16 kilometers per second relative to the Sun, about 31,000 to 36,000 miles per hour, the fastest outbound planetary mission we have flown. Even at that speed, the trip to Pluto took about 9.5 years, almost a decade between launch and arrival. And when it arrived, it did not stop. It did a single high-speed flyby, because slowing down enough to orbit Pluto would have needed far more fuel than we could realistically launch. So we accepted a one-shot pass, a few hours of science after 9 years of flight. So when you say we reached Pluto, the reality is we reached it once, briefly with a small spacecraft, after a huge launch and a long coast. That is what reachable means today for something 5 to 6 billion kilometers away. Now, if that much effort is required for billions of kilometers, what does the next closest star really mean when the star in question is not billions, but tens of trillions of kilometers? Proxima Centauri is the nearest star to the Sun. Its distance is about 4.24 light years. And a light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, around 186,000 miles per second. Multiply that over a year, and 1 light year is about 9.46 trillion kilometers. So 4.24 light years comes out to roughly 40 trillion kilometers, about 25 trillion miles. Going from Pluto to Proxima is jumping from billions of kilometers to tens of trillions, a factor of around 10,000 beyond the outer solar system distances we already struggle with. To see how bad that is, take Voyager 1, the most distant human-made object, moving at about 17 kilometers per second, roughly 38,000 miles per hour. Now imagine you could point Voyager 1 straight at Proxima Centauri and let it go. No extra burns, no slowing down, just cruise. At that speed, it would need on the order of 70,000 to 80,000 years to arrive. Recorded human history is only a few thousand years old. Agriculture is maybe 10,000 years old. So you're talking about a travel time that is longer than the entire existence of civilization. That is what next star over means in practice with current speeds. So side by side, Pluto at billions of kilometers is just within reach of a 10-year sprint and a flyby. Proxima at tens of trillions of kilometers is completely out of reach for anything like a normal mission. And we haven't even mentioned advanced engines yet. This is pure distance and speed. The next issue is that even light itself starts to look slow at these scales. You're used to treating light as instant. You flip a switch, your room lights up. You send a message, it feels immediate. But that's only because Earth is tiny compared to the speed of light. From the sun to Earth, light takes about 8 minutes. The sunlight you see left the sun 8 minutes ago. Now push that to Pluto, and the one-way light travel time from the sun can reach about 5.5 hours. The same applies to radio signals. A command from Earth to a probe at Pluto takes hours to get there, and its reply takes hours to come back. You cannot steer it in real time. Now extend the same idea to Proxima Centauri. At 4.24 light years, even light needs 4.24 years to cross that distance. If you send a radio signal to a probe near Proxima today, it gets that signal a little more than 4 years from now. If it answers right away, you see the reply more than 4 years after that. So one question and one answer take roughly 8.5 years. That is not mission control. That is sending a message and letting almost a decade pass before you know what happened. The probe would have to operate almost completely on its own, with no quick corrections, no fast troubleshooting. Longer distances also mean longer missions, and longer missions mean more time for hardware to age, for radiation to damage electronics, for small problems to accumulate. Even a 10-year Pluto mission has to be designed to survive a harsh environment for a very long time. A Proxima mission at our current speeds would need to survive for time spans that no machine has ever endured. So the core point of this first part is direct. Before you even talk about propulsion, artificial intelligence, fusion, antimatter, or anything exotic, you have to admit that the raw layout of space is already a major barrier. Going to Pluto is at the edge of what we can do, and only as a fast flyby. Going to Proxima with today's speeds and today's mindset is effectively impossible on any human timescale. And remember, this was just about distance, time, and light. We have not yet looked at how your rockets actually perform, and why, compared to the distances you just heard, even our fastest spacecraft are painfully slow. So the next question is simple and uncomfortable. If the distances are this punishing, what happens when you realize your engines are nowhere near good enough to fight them? So now that you've seen how bad the distances are, here's the next uncomfortable question. If Pluto and Proxima are that far, are your rockets actually anywhere near good enough, or are they basically toys on a cosmic scale? On Earth, you're impressed by big speed numbers. Mach 25 sounds extreme. It's the kind of number you hear with space shuttles and missile tests. But space does not care about what sounds extreme to you. It only cares about raw velocity and how hard it is to add more of it. First, you need to know one key number. To escape Earth's gravity completely, you need a speed of about 11.2 kilometers per second, around 25,000 miles per hour. That's the escape velocity. If a rocket can give a spacecraft close to that speed relative to Earth, the spacecraft can break free and head out into deep space. Modern chemical rockets, the ones that burn liquid oxygen and fuel like kerosene or hydrogen, can give a payload on the order of 9 to 10 kilometers per second of delta V. And delta V is just a precise way of saying total change in speed you can get out of your fuel. You stack stages, you add boosters, you burn through a mountain of propellant, and after all that, you're getting under 10 kilometers per second of usable velocity change for your spacecraft. That's enough to get into low Earth orbit, which needs roughly 7 to 8 kilometers per second, and it's enough to push probes to the Moon, Venus, Mars, even Jupiter and Saturn with smart gravity assists. So for inner solar system work, chemical rockets are fine. For Mars, they are okay. For Jupiter, they start to struggle. And once you push out toward Pluto, you're really stressing what this technology can do in a single launch. So if that's the basic limit, how did we even pull off New Horizons? How did we send something to Pluto at all? New Horizons is basically the best example you can use of what chemical rockets can do when everything goes in their favor. It launched on an Atlas V, a very powerful rocket. It used a strong upper stage, and then it stole extra speed from Jupiter with a gravity assist. That gravity trick is basically using Jupiter's motion and gravity to sling the probe faster without burning more fuel on the spacecraft itself. After all the burns and the Jupiter assist, New Horizons ended up moving at roughly 14 to 16 kilometers per second relative to the Sun. That's about 31,000 to 36,000 miles per hour. At launch, it was the fastest object we'd ever thrown out of the solar system. And even with that record speed, it still needed almost 9.5 years to get to Pluto. And remember, it did not stop there. It just flew past, a quick look, and then it kept going into the Kuiper Belt. So when you picture that, understand what best case means here. You take one of the most powerful rockets, you fine-tune the trajectory, you use Jupiter as a free engine, you design the spacecraft to be as light as possible, and the reward is one small robotic probe, one visit, no orbit, roughly a decade of travel time. That's the full power of our current chemical tech on a Pluto mission. Now take that speed and try to scale it to Proxima Centauri. This is where the numbers stop being impressive and start being discouraging. If you take a cruise speed of about 16 kilometers per second, like New Horizons had around the Sun, and you ask how long does it take to go about 40 trillion kilometers, the distance to Proxima, you get an answer on the order of 2.5 trillion seconds, which is something like 80,000 years. So the same performance that barely makes Pluto a decade-long trip turns Proxima into an 80,000-year journey. That's not a mission in any normal sense. That's just throwing a metal object in the void and hoping it's still intact when your entire civilization has changed beyond recognition. You're not planning operations, you're just asking, can this titanium and aluminum box survive longer than Homo sapiens as a species? At this point, it's natural to ask, fine, then just go faster, build a stronger rocket, burn more fuel. What's stopping us from pushing that 16 kilometers per second up to 160 or 1,600 or some huge number? The problem is that chemical rockets don't scale like that. Each extra bit of speed costs much more fuel than the last bit because of how rockets work. There's a very simple relationship in rocketry that says the faster you want your spacecraft to end up, the higher the ratio has to be between your starting mass with fuel and your final mass without fuel. And that relationship is not linear, it's exponential, which means it explodes quickly. In plain language, if you want to add a little more speed, you add some more fuel. But if you want to multiply your speed, you don't just multiply the fuel, you need many times more. To go 10 times faster than New Horizons using the same kind of engines, from around 16 kilometers per second to around 160, you're looking at fuel mass that becomes absurd. Your rocket turns into a giant fuel tank with a tiny payload on top. The launch vehicle starts to look like a skyscraper full of propellant just to send something the size of a car, and even that is still only a small fraction of light speed. So when people say just build a bigger rocket, that's the trap. Bigger does not get you a little farther. It gets crushed by the curve of how fuel requirements grow. You hit practical limits very fast in terms of what you can build, what you can pay for, and what you can even launch off a planet without breaking everything else in the process. But it still feels abstract until you compare these speeds to something your brain can picture. So here's a simple check. A fast racehorse can run roughly 70 kilometers per hour, about 43 miles per hour. That's quick on the ground, and your body understands what that looks like. New Horizons was moving at about 16 kilometers every second. Every single second. That's about 57,600 kilometers per hour, roughly 35,800 miles per hour, more than 800 times faster than that horse. In everyday life, that is insane speed. Nothing you will ever ride or drive comes close to that. It crushes jetliners. It crushes fighter jets. And yet, at that speed, it still took almost a decade just to cross the gap to Pluto. And if you tried to push that same speed to a nearby star, you'd still be flying for tens of thousands of years. That's the real punchline. Your fastest hardware is already far beyond your daily experience. But on the scale of the solar system, it's slow. And on the scale of the galaxy, it's basically standing still. So now you have two stacked problems: huge distances and engines that give you only a tiny slice of the speed you'd actually need. And the uncomfortable part is, this isn't just about trying harder. Simple effort doesn't beat the math that governs rockets. And that math is exactly what we're going to confront next, because behind all of this is one old equation that quietly says no every time you dream about going interstellar. You've seen that distances and speeds are already punishing, but here's the part almost nobody outside rocketry talks about. There is a single, simple idea from 1903 that quietly kills your dreams of going much faster, and it's not out of date. It still runs the show today. It's called the rocket equation, and in plain language, it says this. The maximum change in speed your rocket can give a spacecraft, the total push you get out of all your fuel, depends on two things: how fast the exhaust comes out of your engine and how extreme the ratio is between your starting mass with fuel and your final mass after the fuel is gone. More precisely, your total change in speed equals your exhaust speed multiplied by a logarithm of that mass ratio. And the key word here is logarithm. That means the relationship is curved, not straight. If you want a little more speed, you add some fuel. But if you want a lot more speed, the fuel requirement explodes. Doubling your needed speed is not doubling your fuel. It's far worse. And if you try to chase big numbers, your rocket turns into almost all fuel and almost no payload. So you are stuck between two levers. You can increase the exhaust speed, or you can increase how much of your rocket is fuel. And chemical rockets are bad at both past a certain point. They top out in exhaust speed, and they already spend most of their mass on propellant. That's why this equation is the hidden villain. It locks chemical rockets into a narrow range of performance, and you can't argue your way around it. Let's make that concrete. Chemical rockets, the kind we actually use, have exhaust speeds of only about 3 to 4.5 kilometers per second. That's roughly 2 to 2.8 miles per second. Different propellants and engine designs tweak that number, but they don't change it by a factor of 10. They change it by maybe tens of percent. So your exhaust is leaving the engine a few kilometers per second faster than the rocket itself ends up going. Now plug that into the logic of the rocket equation. Suppose you want your spacecraft to gain a total of around 40 kilometers per second of speed over its mission. That's about what you'd like if you really want to push out into the outer solar system quickly. With exhaust only a few kilometers per second faster than that, your mass ratio, the ratio between full and empty, becomes ridiculous. You end up needing hundreds or even thousands of kilograms of propellant for every kilogram of spacecraft that actually goes anywhere. Before staging, that kind of ratio means absurd vehicle sizes. You would be stacking enormous fuel tanks, huge boosters, and complex structures just to deliver a tiny, fragile payload into deep space. In other words, yes, the math lets you write down 40 kilometers per second, but the engineering reality says good luck building the monster you'd need to achieve it. This is exactly why Pluto sits right at the edge of what chemical rockets can handle, and why New Horizons looks the way it does. To get that probe to a fast flyby, you accept extreme compromises. You design the spacecraft to be as light as possible. You mount it on a giant launch vehicle. You squeeze every bit of performance out of upper stages. And you still lean on gravity assists from big planets to get what is basically free velocity, because you can't carry enough fuel to do it all yourself. And even then, look at what you got. New Horizons approached Pluto at roughly 14 kilometers per second, about 31,000 miles per hour. That was great for travel time, but it meant there was no realistic way to slow down and enter orbit. The delta V you would need to hit the brakes at Pluto is comparable to what you needed to leave the inner solar system in the first place. So the fuel requirement for a full go there and stop mission would have gone way beyond what a single chemical launch could provide. You get one high-speed pass, and then the target is gone behind you. So Pluto is just within reach because we accept the flyby, and we use every trick, from big rockets to planetary slingshots, to make the mission barely work. The equation allows it with careful design, but you can feel that we're sitting at the edge of the envelope. You don't casually repeat this with heavy orbiters and landers. Now stretch that thinking to Proxima Centauri, and you see why people say impossible for now without exaggerating. Imagine we want to cut the Proxima trip from 80,000 years down to, say, 1,000 years. That is still longer than any country or institution has ever lasted, but at least it's on a scale you can talk about. To do that with a straight shot, you need on the order of tens of thousands of kilometers per second, a significant fraction of the speed of light, not 16 kilometers per second, but thousands of times more. Keep the same kind of engine with exhaust coming out at just a few kilometers per second and apply the same rocket equation. To get that much change in speed, the mass ratio you need is effectively impossible. You end up needing more propellant than you could ever realistically launch. The rocket would have to start out so huge, you'd run out of material in the solar system before you had enough fuel. That's not an engineering challenge, that's a hard physical wall set by the math. This is why you can't fix interstellar travel by just making a nicer chemical rocket. Small improvements won't move the needle. You can polish nozzles, you can make tanks lighter, you can improve pumps, you can optimize staging, and all of that is useful for normal missions, but none of it changes the fact that as long as your exhaust speed is only a few kilometers per second, the rocket equation will slam the door on any attempt to reach a big fraction of light speed with a practical vehicle. It does not care how rich your country is. It does not care that your movie concept art looks amazing. It does not care about ambition or slogans. It is just a relationship between mass, exhaust speed, and velocity. And as long as you stay in the chemical regime, you are stuck. Pluto stays barely doable with clever mission design. Proxima stays firmly in the realm of theory and science fiction. So if distance is crushing you and your current engines are locked in by this equation, what's left? Even if you somehow built a probe that could beat those odds, could it actually survive the time it would need to fly? That takes you to the next problem, one that doesn't care about equations at all. It's simpler and more brutal. What happens when your mission timeline is longer than any human lifetime, and maybe even your entire species? You've seen how distance and speed fight you, but here's the part that makes everything worse. Even if you somehow built the perfect probe, time itself is waiting to kill the mission. Think about your own life first. A typical human lifetime is around 80 years, maybe a bit more. That's one person's horizon. Empires usually last a few hundred years at most before they change into something else. That's the timescale your brain is used to, decades, maybe a couple of centuries. Now compare that to deep space missions. A Pluto mission like New Horizons already eats almost 10 years just to arrive, and another decade of planning and building before that. So from early concept to getting the science back, you're looking at 20, maybe 25 years. That already stretches across a big chunk of someone's career, but it still fits inside one lifetime. One group of scientists can design it, launch it, and actually see the results. Now drop Proxima Centauri into that picture. With our current speeds, you're talking about 70,000 to 80,000 years of travel time. That's 3,000 generations of humans. You have no organization, no culture that has ever existed that long. Languages evolve in just a few hundred years. In 1,000 years, they're often unrecognizable. In 10,000 years, they can be completely gone. So when you talk about an 80,000-year mission, you're not just asking, can the spacecraft survive? You're asking, will anything on Earth still exist that remembers why we launched it? And that's before you even look at the hardware itself, because if time destroys institutions and languages, it absolutely destroys electronics and machinery. Take something we actually know, Voyager 1 and Voyager 2. They launched in the late 1970s. They've been flying for almost 50 years. That's already impressive, but you can see the cost. Their power comes from radioisotope generators that decay slowly, so the electrical power available drops year after year. Instruments are being turned off one by one to keep the core systems running. The computers and components have been hit by radiation. They've gone through thermal cycles, they've been struck by tiny dust particles, and mission control has had to do careful workarounds multiple times just to keep them alive. Now imagine asking a spacecraft not to last 50 years, but 500 years. Even that is already 10 times longer than Voyager has gone, or 1,000 years or more. Every capacitor, every transistor, every solder joint, every connector, every piece of insulation becomes a potential failure point. Plastic materials can become brittle, metals can fatigue under temperature changes, lubricants dry out, coatings peel. Over a few decades, you can design around that. Over centuries or millennia, you are in totally unknown territory. You've never built anything that stays powered and functional that long without maintenance. Then there's the software, which sounds abstract but is just as vulnerable. Digital electronics in space are constantly being hit by energetic particles, cosmic rays, solar particles. When they pass through a chip, they can flip a bit, turn a 0 into a 1 or a 1 into a 0. That's called a single event upset, and we already see it on satellites and probes. We handle it today with radiation-hardened components, error-correcting memory, redundant systems, watchdog timers that reset the computer if something goes wrong, and regular software updates from Earth. A Mars rover gets patched, reprogrammed, sent new routines. Engineers can react within minutes or hours when something weird happens. Now stretch that to interstellar distances. If your probe is a few light years away, a single round trip for a signal can be 6 to 8 years or more. You send a command, you wait years, you see what happened, you send the fix, you wait more years. That is not real-time control. It is more like sending a letter to the future and hoping. So the spacecraft has to run almost completely autonomously, and it has to do that while random bit flips slowly try to corrupt its software over decades or centuries. Even with very good error correction, tiny failure probabilities add up over millions of hours. A 1 in a billion chance per hour stops being rare when you multiply it by hundreds of years. At some point, the probability that something important breaks approaches 1. So the question becomes, can you design a system that not only survives damage, but can actually repair or reboot itself in smarter and smarter ways, without anyone back home holding its hand? And then there's the part people really don't like to think about. Even if you solve the physics and the engineering, who actually keeps paying attention to this thing over centuries, over thousands of years? Institutions are not permanent. Countries split, merge, collapse. Companies get bought, go bankrupt, or become irrelevant. The idea that NASA, as you know it today, will still exist in anything like its current form in the year 2400, let alone the year 82,400, is not realistic. Ask a simple question. Who signs off on the operations budget in year 350 of a mission? Is there a space agency? Is it some global organization? Is it a private foundation set up just for this probe? Over hundreds of years, you must assume wars, economic crashes, shifting priorities. Even if the yearly cost is small, multiply that by centuries and it becomes huge. This is not just physics anymore. This is sociology and economics, long-term human behavior, and we have no proof we can keep a single project funded and supported for more than a few generations. When you look at Pluto again with this in mind, you see why it is just barely okay. A Pluto mission fits into a single scientific career. A team can propose it, design it, launch it, and still be around when the data comes back. The institutions involved don't have to survive for centuries. They only need to stay stable for a few decades. Space agencies can justify that to taxpayers and governments. It feels long, but not absurd. Proxima is the opposite. Even if you brought the travel time down from 80,000 years to something like 1,000 years, you're still asking multiple civilizations in a row to keep caring about an object they will never see, to pass down records, language, protocols, funding, and technical knowledge for generation after generation. You are asking humans to build a machine that nobody alive at launch will see complete its journey. Not their children, not their grandchildren, not their distant descendants. We have never done that. We have cathedrals and monuments that took centuries to build, but they still stayed within a human time frame, and they did not depend on fragile electronics flying through radiation and vacuum. So right now, time is not just a number on a mission plan. It is a hard barrier. It attacks your hardware, your software, your organizations, and your ability to care over long periods. And remember, all of this is happening in a universe that is actively hostile to your machines. Radiation, dust, extreme cold, impacts. All of that is chewing away at your spacecraft while the clock runs. So the next question is, even if you somehow accept the insane timescales, Can your probe actually survive the environment it has to cross? Because outside Earth's shield, space is not empty and peaceful. It is constantly trying to break what you send into it. You might think that once you've built a tough probe and accepted the crazy travel time, the hard part is over. But out beyond Earth's shield, just existing in space becomes a long, slow fight for survival, and the vacuum itself is actually the easiest part of that fight. The moment you leave Earth's magnetic field, you lose your natural armor. You're now exposed to a constant rain of high-energy particles from the sun and from the galaxy itself. These are galactic cosmic rays and solar energetic particles. Missions like Voyager and New Horizons carry detectors that measure them, and the numbers are not gentle. Your electronics are being hit over and over for years. Every one of those hits can do damage. Sometimes it's a single bit in memory flipping from a 0 to a 1. Sometimes it's a latch-up, where a chip temporarily misbehaves or locks. Over decades, this adds up. It's not one big event, it's the accumulation of thousands or millions of tiny insults to your hardware. You can add shielding, layers of aluminum or plastic materials like polyethylene, and that does help. It reduces the amount of radiation that reaches sensitive components. But shielding is heavy. Every extra millimeter adds mass, and mass is exactly what you struggle with when you design any deep space mission. More mass means more fuel, more cost, and more stress on your launch vehicle. So you're stuck in a trade-off. Do you give the spacecraft thick armor and pay a massive penalty in launch requirements, or keep it light and accept higher radiation risk? For a decade-scale Pluto mission, you can compromise. You design for maybe 15 or 20 years of survival, you test the electronics, you harden the most critical parts, you accept that some instruments will eventually fail. For Proxima-class speeds and timescales, that entire strategy breaks. You haven't even proven you can build electronics that stay healthy for that long on Earth, let alone under constant radiation. And that's just the invisible stuff. What about actual physical impacts? What happens when you start slamming into dust at tens or thousands of kilometers per second? Interplanetary space is not perfectly clean. There are dust grains and micrometeoroids, some smaller than a grain of sand and some bigger. Near Earth, these are already a concern. Satellites get tiny impact marks and pitting over the years, at orbital speeds of a few kilometers per second. Now, imagine you're moving at 50 kilometers per second, over 110,000 miles per hour, like a very fast deep space probe might during a gravity assist or an aggressive trajectory. A tiny grain hitting you at tens of kilometers per second behaves more like a small bullet than a dust mote. Now push that to interstellar ambitions. If you ever reach 10% of the speed of light, around 30,000 kilometers per second, about 67 million miles per hour, even microscopic particles carry explosive amounts of energy when you hit them. A tiny grain can release energy comparable to an explosive charge when it hits your hull. Your spacecraft would need extremely strong shielding, or clever ways to deflect or vaporize dust in front of it, otherwise it gets sandblasted to death long before it reaches another star. For Pluto-class missions at 14 or 16 kilometers per second, you can design modest armor, maybe put the most sensitive parts behind tanks or structural elements. You still take impacts, but the risk is manageable over a decade. For Proxima-class speeds and timescales, shielding becomes a nightmare. You need layers that may be meters thick, or active magnetic or plasma shields, all of which add complexity and mass you can barely afford. And while all of that is happening, your spacecraft is also dealing with temperature extremes that are nothing like what you face in your Earth. So the question is, how do you keep something at a safe temperature when the sun fades from a bright lamp into a cold, distant star? Near Earth, at 1 astronomical unit, sunlight delivers about 1,360 watts per square meter. That's like having more than a kilowatt of power hitting every square meter of surface. You can use that for solar panels, and your thermal design assumes a strong, steady source of heat. At Pluto's distance, around 30 to 50 AU, that solar flux drops by a factor of roughly 900 to 1,000 because it falls off with the square of the distance. By then, sunlight is a weak, dim glow, not a powerful heater. Your spacecraft sits in a deep freeze, surrounded by objects only a few tens of degrees above absolute zero. Your electronics have to stay warm enough to function, so you rely on internal heaters and the waste heat from your power source. This creates a harsh cycle. Parts of the spacecraft can be very cold when systems are off, then warm up when powered, then cool again. Over years, this thermal cycling stresses materials. Different parts expand and contract at different rates. Joints can weaken, cracks can form, solder can fatigue. For a 10 or 20-year mission, you can test and design around this. For 200 or 2,000 years, you have no real data, you're guessing. And in all of this, remember, there is no rescue team. If a Mars rover has a problem, you see it within minutes or hours. You can send new commands, try different modes, switch to backup systems. And in low Earth orbit, if a satellite is important enough, you can even send astronauts to repair it. We've done that with Hubble. At Pluto, your spacecraft is 4 to 6 light hours away. A command you send now arrives hours later. Its response comes back hours after that. You cannot drive it moment by moment. You send sequences of commands and you hope they work. If something goes wrong at a critical moment, you might find out too late to fix it. At Proxima distances, this delay stretches to years. You're not doing mission control anymore. You're sending one-way instructions to an almost autonomous robot. And if it gets into serious trouble, there is no realistic way to repair or reset it from Earth. So put all of this together. Radiation slowly degrading electronics, dust and micrometeoroids chipping away at your structure, extreme cold and temperature swings stressing every material, and no real-time control or rescue option. Every extra year your mission runs, the probability grows that some random event ends it. For a Pluto mission, you ask the spacecraft to survive maybe 10 to 15 years of this. That is already tough, but it's just on the edge of what we've learned to do. For a Proxima mission, you'd be asking it to survive for centuries or even millennia, flying through environments we've barely sampled, with technology that has never been proven on anything close to that timescale. The chance that nothing critical fails somewhere along that timeline drops sharply, long before you ever reach another star. And we haven't even talked yet about one of the most basic needs of any spacecraft: power. Out in the dark, far from the sun, how do you keep the lights on, keep the instruments running, keep the transmitter alive? When solar panels fade and batteries run dry, that's the next barrier, because you can't just throw more batteries on and hope for the best. You've seen how distance, time, and the environment all push back, but there's another simple question that turns brutal very fast. How do you actually power a starship in the dark? Because you can't just strap on extra batteries and call it a day. Everything a spacecraft does needs energy: heating, computing, pointing its antenna, running instruments, sending data back home. Near Earth, you mostly solve this with solar panels. The sun is bright, you unfold some arrays, and you get useful power. But that whole strategy collapses as soon as you go out far. The basic rule is simple. As you move away from the sun, the intensity of sunlight drops with the square of the distance. If you go twice as far, you only get 1/4 of the light per square meter. At 3 times the distance, you're down to 1/9. So by the time you move from 1 astronomical unit, Earth's distance, out to about 30 AU, around Pluto's neighborhood, the sunlight is weaker by a factor of roughly 900 to 1,000. That means a solar panel that gives you, say, a kilowatt near Earth might only give you a few watts out by Pluto, if that. To make up for that, you'd need solar panels thousands of square meters in area, which means huge, heavy, fragile structures, hard to launch, hard to deploy, and hard to keep stable over a 10-year journey. And that's for Pluto. On a Proxima trip, you spend almost the entire flight in interstellar space, so far from any star that sunlight is basically useless. There is simply no practical amount of solar panel you can carry to fix that. So if solar dies with distance, what do you use instead? For outer solar system missions, we already have an answer. We use nuclear power. Not reactors, but radioisotope thermoelectric generators, RTGs. These are solid-state power sources that use the heat from the decay of a radioactive material, usually plutonium-238. That heat is turned into electricity with thermocouples. No moving parts, very simple and robust. An RTG might start out producing a few hundred watts of electrical power, enough to run a small spacecraft, heaters, and instruments. But the power does not stay constant. Plutonium-238 decays over time, roughly on the scale of decades, and the electrical output drops by around 1% per year, sometimes a bit more when you include degradation of the thermocouples. After 10 years, you might still have most of your power. After 30 or 40 years, you've lost a big fraction. After 100 or 200 years, the output is so low that it's effectively dead for any serious mission. For a Pluto probe, this is fine. You need around a decade of cruise plus some years of operations, maybe 20 or 30 years of usable power in total. RTGs can handle that. But for a Proxima probe, even if you somehow cut the travel time down to a few hundred years, your RTG will be out of juice long before you arrive. You basically launch with a power source that is guaranteed to fade away while you're still nowhere near the target. So people look at a more powerful nuclear option: reactors. Small nuclear fission reactors in space could, in principle, give you kilowatts or even megawatts of power, far more than an RTG. Enough to run strong electric thrusters, radars, high-power transmitters. It sounds like the obvious solution, but it comes with major problems. A reactor is not a simple brick of hot material. It needs control systems to keep the reaction stable. It needs cooling systems to dump excess heat into space, usually with large radiators. It needs shielding to protect the rest of the spacecraft from radiation. All of that adds mass and complexity. And every extra pump, valve, sensor, and electronic controller is another thing that can fail over time. On Earth, we run reactors with human operators, regular maintenance, inspections, and repairs. Even then, we struggle to keep them perfect over decades. Now imagine you want a compact space reactor to operate with no maintenance, no repairs, and minimal adjustments for centuries, in deep space, with only software and backup systems to keep it in line. That is a level of long-term reliability we have never demonstrated. So right now, reactors are promising on paper, but not proven on the kind of timescales an interstellar mission needs. To get around both fuel and onboard power, there's a more radical idea: beamed power. Instead of carrying huge amounts of propellant and big energy sources on the spacecraft, you accelerate a very light craft using energy sent from home. For example, a laser sail. You take a thin, reflective sail attached to a small payload and hit it with a powerful laser from Earth or from a large station in space. The pressure of the photons pushes the sail and slowly accelerates it to a large fraction of light speed. No heavy engine or big propellant tank on the probe itself. This is attractive because it sidesteps some of the mass problems. The engine stays at home, but it creates a different monster. You need a laser system capable of delivering gigawatts or even tens of gigawatts of power, focused on a target thousands or millions of kilometers away. You need enormous optics, giant mirrors or lenses. You need precise tracking so the beam stays on the sail as the craft accelerates and the distance grows. Any misalignment and your sail is no longer being pushed effectively. And that's just to launch it. After the acceleration phase, you still need some power on board for instruments and communication. So even beamed sail concepts don't fully remove the power problem. They just move most of the heavy lifting to gigantic infrastructure that does not exist today. Building and running that kind of system is beyond our current industrial and financial capacity. When you put all this side by side, you see why Pluto looks like the upper limit for what we can do right now. New Horizons and similar probes can run on RTGs for the decade or two they need to cruise and then operate briefly at the target. The power decline is manageable over that window. The spacecraft doesn't have to stay alive for centuries, and solar is only a small bonus in the inner solar system, not the main source. Try to push beyond that into hundreds of years of flight, and RTG output fades away. Batteries are useless on that timescale. Reactors are not yet mature enough for fully autonomous century-long operation, and beamed power requires planetary-scale infrastructure we simply don't have. So power becomes another hard wall. Pluto is in range because our current nuclear power sources can just barely support decade-long missions. Proxima is out of range because we don't have anything that can feed a spacecraft reliably for the time it would actually be in flight. And without power, everything else fails. Your heaters, your computer, your transmitter, your sensors all go dark. And even if you somehow solve power, another problem waits for you. You're not just throwing a probe into space and hoping it hits something. You have to aim it, steer it, and meet a moving target that is tiny compared to the distances involved. So the next question is, how do you actually hit a world the size of Pluto or a planet around Proxima when you fire from billions or trillions of kilometers away and you only get one shot? You've seen how hard it is just to power and protect the probe, but there's another problem that sounds simple and is actually brutal. How do you even hit the target in the first place when space is huge and what you're aiming for is tiny? Start with Pluto, because if hitting Pluto is already hard, you can guess what happens when you try to hit another star system. New Horizons did not just go to Pluto. It had to intercept a small dwarf planet that's much smaller than our moon, tens of astronomical units away, while both Earth and Pluto were moving around the sun at tens of kilometers per second. Earth is orbiting about 30 kilometers per second, Pluto at around 4 to 5 kilometers per second, and your spacecraft is on its own track at around 14 to 16 kilometers per second. Everything is moving, nothing is fixed. To make that work, mission planners had to compute a trajectory years in advance, so that after about 9.5 years, New Horizons would pass through a tiny slice of space at the exact moment Pluto happened to be there. If it arrived a little early or a little late or a bit off to one side, the distance between the spacecraft and Pluto could easily be tens or hundreds of thousands of kilometers, and that is enough to turn a detailed flyby into a useless miss. So during flight, you do mid-course corrections, small burns, sometimes changing the speed by just a few millimeters per second or a few centimeters per second. That is a tiny nudge, but over billions of kilometers of travel, that nudge shifts the final aim point by huge distances. That's how sensitive it is. Small tweaks early, huge effects later. Now, take that basic idea and push it out to Proxima Centauri. This is not just more of the same. The difficulty explodes. Proxima is not sitting still either. It's moving through the galaxy. The sun is moving too. Both systems are orbiting the center of the Milky Way at tens of kilometers per second. If your travel time is tens of thousands of years, the star's position relative to the sun changes a lot during the flight. So you don't aim at where Proxima is now, you aim at where it will be in 40,000 or 60,000 or 80,000 years, and you have to predict that motion accurately. Any small error in that prediction or in your initial trajectory keeps growing the whole way. A tiny fraction of a degree of error in your aim, which sounds like nothing, can turn into missing the entire star system by billions of kilometers when you finally cross that region of space. There's no easy swing back around and try again. You're going so fast and the distances are so large that a miss is basically permanent. And there's another catch. You also don't have the same navigation tools as you do near Earth. Close to home, you can use GPS, ground radar, constant radio tracking from multiple antennas. You can correct your orbit around Earth or the Moon with frequent feedback from the ground. The signals are strong, the delays are short. By the time you're at Pluto distances, that support fades. The only way to know exactly where your spacecraft is and where it's going is to use the Deep Space Network, giant radio dishes on Earth that listen for tiny signals and measure their timing in Doppler shift, combined with the spacecraft's own star trackers, cameras that look at the sky and compare star patterns to an onboard catalog. Farther out, beyond the heliosphere, even that gets harder. The signal is weaker, the background noise changes, and you have to start thinking about using pulsars as natural navigation beacons. Pulsars are neutron stars that emit extremely regular pulses of radio or X-ray light, like cosmic lighthouses. By measuring the arrival times of these pulses from several pulsars, a spacecraft can triangulate its position. Basically a deep space version of GPS, but with distant neutron stars instead of satellites. It's an elegant idea, and experiments show it can work, but it's not simple. Your instruments have to be stable and sensitive for decades. Your timing has to be incredibly precise, and your software has to interpret all of that without mistakes. Because if the navigation solution is off, your course corrections will be wrong too, and you might not spot the error until it's huge. Then there's the problem of what happens when you actually reach the target. Even at Pluto, if you're flying fast, you don't hang around very long. New Horizons had just hours around closest approach to grab most of its high-resolution images and measurements. After 9.5 years of cruise, the main science event was effectively one long pass. Once that window closed, Pluto shrank back into a dot. Now imagine a Proxima mission where you somehow get the probe up to 10% of the speed of light, around 30,000 kilometers per second, about 67 million miles per hour. That's the kind of speed you'd want to bring the travel time down to decades instead of millennia. At that speed, the planetary region around Proxima, the zone where any planets and interesting stuff sit, would be crossed in hours or less. If you don't slow down, you get a blur. You grab whatever data you can while you rush past at an insane velocity, and then you're gone. You don't get to turn around. You don't get another pass. It's one shot, one opportunity. And if your aim is off, you might not even pass close enough to get useful data in that tiny time window. To actually stop, to go into orbit around the planet or even around the star, you need a second set of huge velocity changes, as big or bigger than what you used to speed up in the first place. That means more propulsion, more fuel, or another beamed braking system on the far end, which makes the rocket equation and the power problem even worse than they already are. So for Pluto, navigation and a lack of braking delta-v are painful, but still manageable. You can live with a fast flyby, because even one close pass gives you a massive science return. You can plan your corrections, your timeline, and your instrument sequences around a predictable encounter in a time frame humans can handle. For Proxima, the same issues blow up into something close to impossible. You have to predict and hit a moving target system over distances measured in trillions of kilometers. You have to navigate mostly autonomously with sensors that must not fail over decades. You have to align a tiny spacecraft with a tiny planetary system, and then either accept a razor-thin flyby window or somehow break from a large fraction of light speed with technology we do not have. And underneath all of that is the same ugly truth. Small errors early become huge errors later. Close enough does not cut it when you've flown for thousands of years across interstellar space. If you're not almost perfect, you miss. And we do not build perfect systems. We build systems that are good enough for a decade or two of operation, tuned for missions where we can adjust and correct as we go. So now you're in a worse position. The distances are cruel. Your rockets are limited by old physics. Time slowly destroys both your machines and your institutions. Space itself attacks your hardware with radiation and impacts. Power runs out. And even if you somehow survive all of that, you still have to hit a tiny moving target with near perfect accuracy. And we haven't even talked about something you absolutely need if this is going to be a mission and not just a stunt. You have to talk to the probe, send commands, get data back, run an actual conversation across these distances. So the next question is, what does it really mean to communicate with something at Pluto, and what changes when that something is sitting 4 light years away? You already know how annoying it is when your Wi-Fi dies going through one concrete wall. Now stretch that idea across billions or trillions of kilometers, because space communication is basically that problem turned up to a ridiculous level. And the first thing that breaks is your intuition for how fast and how strong a signal feels. Start with signal strength. When you send out radio waves from a spacecraft, they don't travel in a straight, narrow beam forever. They spread out. Imagine them expanding as a growing sphere around the spacecraft. The surface of that sphere gets bigger and bigger with distance, so the same total power has to cover more and more area. The result is, if you double the distance, the power per square meter drops to a quarter. Go 10 times farther, and it's down to 1/100th. Near Earth, that's not a big deal. A few watts from a satellite is plenty. Your ground antennas are close, the signals are strong. At Pluto distances, tens of astronomical units away, it's completely different. A small spacecraft transmitting with a few watts is whispering into a hurricane. By the time that signal reaches Earth, it is insanely faint. You need huge 70-meter dishes like the ones in NASA's Deep Space Network just to catch a tiny fraction of those photons. Because of that, the data rate collapses. Near Earth, you can get megabits per second. You can stream video, send big dumps of data. At Pluto, you're often down in the kilobits per second range, or even less, just to keep the signal clean enough to be readable. That means a single high-resolution image can take hours to transmit. New Horizons took months to send home all its Pluto data, not because it didn't have the files ready, but because the radio link was so weak at that distance. That's Pluto. And Pluto is close compared to Proxima Centauri. So now think about what happens when you try to talk across light years. Communication isn't just about strength, it's about delay. For Pluto, a radio signal moving at the speed of light takes several hours one way, depending on where Pluto is in its orbit. You send a command, you wait maybe 4 to 6 hours to see the response. That's slow. It means you can't joystick the probe live, but you can still run interactive operations on human timescales. You can send a sequence in the morning and see how it went in the evening. For Proxima Centauri, that whole model dies. At 4.24 light years away, even light takes 4.24 years to get there. You send a signal today, the spacecraft hears you more than 4 years from now. If it answers immediately, you see that reply more than 4 years after that. You're looking at around 8.5 years for a full ask and answer cycle. You will not be doing real-time troubleshooting. You will not be testing new commands on the fly. You send instructions and then you age almost a decade waiting to learn if they worked. So the mission cannot depend on constant back and forth. The spacecraft has to make almost all of its decisions by itself, including what data to send, what to compress, what to discard, and how to handle anomalies. Because by the time your fix arrives from Earth, whatever went wrong will either have resolved itself or already killed the mission. Now stack the strength problem on top of the delay. Talking from Proxima means her transmitter is not just far, it is unbelievably far. To get a decent data rate across that distance, you either need a transmitter on the spacecraft that is much more powerful than anything we've flown, plus a very high gain antenna and perfect pointing, or you need receiver arrays back home that make today's deep space network look small. In reality, you'd need both, and even then, the data rate might only be a few bits per second if you want a decent signal-to-noise margin. That means forget about high frame rate video. Forget about huge streams of raw data. You're not watching alien sunsets in real time. You're counting individual photons arriving at your detectors and decoding tiny patterns, waiting hours or days just to pull out a small block of information. Every bit is precious, and every transmission window has to be planned extremely carefully. On top of that, the way you talk has to change. Communication protocols for an Earth-orbiting satellite assume short delays and stable infrastructure. If something goes wrong, you resend, you reconfigure the ground stations, you update software, you have constant human supervision. For a Proxima probe, your protocol has to survive decades of drift and clocks, changes in the radio environment, upgrades and replacements of ground hardware, and potential new types of interference we haven't even met yet. The spacecraft also has to keep its antenna pointed at Earth with insane precision. Remember, both Earth and Proxima are moving. They're orbiting their own stars, and those stars are orbiting the galaxy. From the probe's point of view, the tiny dot that is Earth moves slowly across the sky over years. The beam of a high-gain antenna is narrow, like a spotlight, not a floodlight. If you're off by a tiny angle, your signal misses Earth entirely. So attitude control and pointing have to be accurate and reliable over absurd timescales. All of this adds up to a harsh conclusion about what an interstellar mission actually is. A mission to Pluto still feels like a very slow remote control robot. You send commands, you wait a few hours, you get data, you adjust. The people who launched the probe can see the results, talk about them, and react. It's delayed, but it's recognizable as operations. An interstellar mission is nothing like that. It's closer to throwing a bottle with a message into the ocean, except the ocean is 4 light years across. You launch a probe, you program it with everything it needs to know, you build in as much autonomy as you can, you point it in the right direction, and then, in practical human terms, you let go. You hope that centuries later or longer, someone is still around, still listening on the right frequencies, still understanding the encoding, and still caring enough to interpret whatever comes back. That is completely different from any mission we currently run. It is not a controlled experiment with active human oversight. It's a one-shot, fire-and-forget scientific gamble. And that shift alone is enough to make space agencies hesitate, because it doesn't fit the way we design, fund, and operate missions today. And remember, we've been talking about uncrewed probes this whole time, machines that don't need food, air, or protection from long-term psychological stress. If just talking to a robotic probe at Proxima is already this hard, what happens when you put humans on board, who need constant life support, protection from radiation, and answers faster than once every 8.5 years? So far, we've only been talking about metal boxes in the dark, and even that already looks almost impossible. Now imagine putting actual humans inside one of those boxes, with bodies that age, that get cancer, that need air, water, food, sleep, and answers faster than once every few years. Suddenly, hard turns into no chance with what we've got. Start with the most basic clash: human lifespan versus travel time. Say you somehow build a crewed ship that can reach 1,000 kilometers per second. That's about 2.2 million miles per hour. This is way beyond anything close to current tech, but let's just pretend you can do it. That speed is still only around 0.3% of the speed of light. Proxima Centauri is about 4.24 light years away, so at 0.3% of light speed, you're looking at over 1,300 years of travel time, more than a millennium locked inside a starship. To get there in one human lifetime, say 40 or 50 years of actual cruising, you need at least 10% of light speed, around 30,000 kilometers per second, roughly 67 million miles per hour. No engine we have or are even close to building can accelerate a crewed, heavily shielded, life support equipped ship to that speed and then slow it down again at the other end. The energy, the propulsion system, and the engineering challenges are completely outside the chemical, nuclear, or electric propulsion we've actually flown. So right away, you're stuck with a choice. Either you accept travel times far longer than any one human life, which means a multi-generational ship, or you admit that with today's tech, even just sending people is off the table. And that's before you hit the next wall: radiation. Outside Earth's magnetic field and atmosphere, space is loaded with high-energy particles, cosmic rays from the galaxy, and bursts of solar particles from flares and coronal mass ejections. On the International Space Station, astronauts are still partly protected by Earth's magnetic field. On a Mars mission, they take a dose that pushes against long-term safety limits over a couple of years. Stretch that to decades, and you're almost guaranteeing serious radiation damage, cancers, nervous system problems, and other health issues. To keep a crew within acceptable dose levels for, say, a 30-year or 100-year trip, you'd need serious shielding, not a thin metal wall, but meters of material around the habitat. The best candidates are things like water or regolith, because hydrogen-rich materials are good at slowing down charged particles. But that means huge amounts of mass. Think of surrounding your crew module with a thick shell of water tanks or packed rock. Tons and tons of it, wrapped around the living space. And that mass loops you straight back into the propulsion nightmare. Every extra ton of shielding is more you have to accelerate and decelerate, which means more fuel, bigger engines, or even more exotic propulsion. It's a vicious circle. To protect humans, you add mass. To move that mass, you need more propulsion. To get that propulsion, you need bigger systems, which again add mass. Then there's life support. Keeping humans alive for a few days in space is already non-trivial. Keeping them alive for months, like on the ISS, takes a few hundred tons of station with constant cargo runs bringing food, water, spare parts, and equipment. The ISS still vents waste, still relies on Earth for resupply, and still needs regular maintenance by visiting crews. A generation ship would have to be a fully closed ecosystem. Air, water, and nutrients constantly recycled, waste turned back into food inputs, plants or other systems providing oxygen. You'd need medical facilities, laboratories, manufacturing capabilities for spare parts, and a way to maintain and rebuild critical systems without help from Earth. Not for a year, not for 10 years, but for centuries, possibly more than 1,000 years if you're not hitting relativistic speeds. That's not a spacecraft, that's a mobile world with a mass and complexity many orders of magnitude above anything we've put into orbit. You're talking about something vastly bigger and more complicated than the ISS, built to operate without resupply forever, with every essential system doubled or tripled for redundancy, and all of it has to survive radiation, micrometeoroids, thermal stress, and internal wear and tear over timescales we have never engineered for. And humans are not just biology, they're psychology, societies, and culture. Even if you solve propulsion, shielding, and life support, you still have to keep a human community stable and functional for generations in a closed metal environment, with no way out and no direct contact with Earth beyond faint, delayed signals. Over hundreds of years, social structures drift, norms change, conflicts grow and fade. You need some way to handle governance, education, conflict resolution, and long-term planning. You'd need to prevent dangerous power imbalances, mass depression, or violent breakdowns, and you'd need to manage genetic diversity and health over a small population, avoiding inbreeding and inherited disorders. It's entirely possible that by the time the ship reached Proxima, the descendants of the original crew might not care about the mission at all. Their entire life experience would be the ship itself. The destination would be an abstract idea from old records, maybe treated as myth or irrelevant history. That's not a physics failure, that's human behavior, and it's even harder to predict and control than cosmic radiation or fuel usage. Now rewind back to Pluto for a second and look at how we actually operate. Pluto is just barely within reach for robots. New Horizons had no crew. It needed no air, no food, no radiation shielding beyond what its electronics required, no complex life support. It was a small, tightly designed machine, sleeping for most of its journey, waking up for key phases, and even that stretched our capabilities and budgets over decades. A crewed Pluto mission would already be extreme. You'd need heavy shielding against radiation in deep space, a life support system that works for years without failure, a propulsion system capable of getting not just a small probe, but a large habitat and return vehicle out there and back. The mass and cost would skyrocket. The risk would be enormous to justify it, and we're nowhere near doing that in reality, which is why Pluto has only ever seen robots. So when you jump from Pluto to Proxima, you're not just adding distance, you're multiplying every human factor. Propulsion, shielding, life support, psychology, medicine, engineering reliability all have to jump from survive a few years to survive centuries or more, without external help, in an environment we still barely understand. That's why right now, Proxima with humans on board isn't just ambitious, it's basically science fiction. It sits in a category we can't even prototype yet. And that's before we talk about the final layer that quietly decides what actually gets built and what stays as pretty concept art: money, industry, and whether our civilization is even willing to pay the price of trying something this big. You've seen that physics itself is already saying slow down, but there's another layer that quietly decides what actually happens. Even if the math and engineering allowed a Proxima mission tomorrow, your economy probably wouldn't. Start with real numbers from things we've actually built. New Horizons, the Pluto mission, cost on the order of a few $100 million for the spacecraft and operations. Once you add the cost of the Atlas V5 launch, you're in the ballpark of around $700 to $1 billion total. That's already a major science mission. Then look at something like the James Webb Space Telescope. JWST ended up around $10 billion, spread over many years and many partners. That is what flagship means in space science. Huge international effort, decades of work, serious commitment, and a budget that has to be defended over and over again. So those are your benchmarks. Roughly $1 billion for a deep solar system probe, around $10 billion for a once-in-a-generation observatory. Now scale up to interstellar ideas, even just the plausible ones, and the costs jump into a different category entirely. If you talk about something like a beamed sail mission, where you push a very light probe with a laser, realistic studies suggest you'd need laser power in the range of gigawatts to tens of gigawatts to get a probe to a decent fraction of light speed. Tens of gigawatts is comparable to the output of dozens of large nuclear power plants, and that energy has to be delivered in a controlled, focused way, with huge optics and precise steering. Building that kind of infrastructure is not slightly more than JWST. It's likely in the trillions of dollars. You'd need massive ground-based or space-based power generation, giant laser arrays, vast mirrors or lenses, a control system that can manage all of it safely. And then you'd need to operate it for years just to accelerate a few small probes. That's what a serious interstellar push looks like, a project at the scale of major national power grids, but dedicated to just one mission architecture. And that's before you consider the opportunity cost. Every dollar spent on a Proxima attempt is a dollar not spent on other things. Climate change mitigation, healthcare, energy infrastructure on Earth, nearer-term space projects like Mars bases, moon industry, asteroid mining, or huge telescopes that can scan thousands of exoplanets from home. Convincing societies to put multi-trillion-dollar sums into something that might pay off in 500 or 1,000 years with no guarantee of success is not a technical problem. It's cultural. Even ambitious national programs rarely survive unchanged for more than a generation. And here, you're asking them to fund something that nobody alive at launch will live to see finished. Even if the money and will somehow appear, you run into the question of industrial capacity. Can we physically build and launch the hardware at the scale needed? Right now, the total mass we launch to orbit every year worldwide is on the order of a few thousand tons. Rockets from all agencies and companies combined add up to that. For a serious Proxima effort, especially if you're talking about multiple probes, big sails, nuclear reactors, huge stacks of propellant, and a full support infrastructure, you'd need to build and loft thousands of tons of precision equipment, not once, but year after year for decades. Big laser arrays or beamed power stations might need tens of thousands of tons of hardware in high orbit or on the moon, plus constant maintenance and upgrades. So you'd have to multiply our current launch capacity by a large factor and keep it there, not for a few years, but for entire human generations. And you'd need the factories on the ground to match that, churning out advanced components at a rate we've never seen for space hardware. That means new heavy industry, new supply chains, and a workforce and education system tuned specifically for that kind of long, intensive project. Compare that to Pluto. New Horizons was not cheap, but it was manageable for a single major space agency with some international help. It fit within a national budget, and the required industrial base was basically an extension of what we already had: medium to heavy rockets, spacecraft factories, nuclear fuel production for RTGs at modest levels, deep space antennas that already existed for other missions. A Proxima-scale project is different. It's not a mission in the usual sense, it's a civilization-scale program. You'd need long-term global coordination, multiple countries committing money, industry, and capital across many decades, with a clear shared goal and a willingness to keep funding it even when everything on Earth is changing: economies, cultures. Right now, we can't even maintain perfect cooperation on far easier problems. We argue over climate, over energy, over relatively small science budgets. Getting the world to agree to spend trillions on a project that has no payoff within any current leader's lifetime is far beyond. So for the moment, Pluto sits near the financial and industrial ceiling of what we can actually do in deep space. One or a few $1 billion for a high-risk, high-reward robotic mission launched on rockets we already know how to build, using nuclear power sources we already know how to assemble, supported by ground systems we already maintain for other probes. A Proxima scale project sits in a completely different class. It demands money, infrastructure, and global coordination at a level we only see in total war or in completely restructured future economies. Even if the physics lined up perfectly, the economic barriers alone keep it in the not yet box. And as if all of that wasn't enough, there's another wall waiting when you try to go from fast to really fast. Because even if you somehow built the lasers, the rockets, and the reactors, the energy bill for pushing a probe to a decent fraction of light speed is enormous. So the next question is simple and brutal. What does it actually cost in raw energy to make even a small spacecraft go at 10% of light speed? And how does that compare to everything humanity uses in a day? When someone says just go at 10% of light speed, it sounds like you're only changing the number on the speedometer. But the real killer is not the speed itself, it's the energy bill that comes with it. There's a simple rule from physics. The kinetic energy of a moving object, the energy it has just because it's moving, depends on its mass and the square of its speed. Not just the speed, the square of it. Double the speed and the energy goes up by 4 times. 10 times the speed and the energy goes up by about 100 times. So as you push toward extreme speeds, the energy requirement explodes. Take a very modest Starship probe, say 1,000 kilograms, about the mass of a small car. Now you want that probe to cruise at 10% of the speed of light. Light travels at about 300,000 kilometers per second, so 10% of that is around 30,000 kilometers per second, roughly 67 million miles per hour. Plug those numbers into the energy relationship and you get a kinetic energy on the order of a few times 10 to the power of 17 joules. You can think of that as a few hundred quadrillion joules. How big is that? Compare it to us. Humanity as a whole runs on a continuous power of something like 10 to 20 trillion watts. If you multiply that by the number of seconds in a day, you're in the ballpark of 10 to the power of 19 joules per day. So accelerating that 1-ton probe to 10% light speed eats up a noticeable fraction of everything our civilization uses in many hours, close to a day. And that's only for one probe and only for the acceleration, not counting losses, inefficiencies, or braking at the other end. Another way to feel it, think about nuclear bombs. A large thermonuclear weapon releases on the order of 10 to the power of 17 joules of energy when it detonates. So a 1,000 kilogram probe at 10% light speed is carrying kinetic energy comparable to several of those large bombs combined, just in the motion of the spacecraft. If you somehow crash that probe into something at that speed, the impact would be a multi-bomb level event. All of that energy had to be generated, focused, and transferred into the spacecraft during acceleration. So when someone casually says, let's just accelerate a probe to 0.1 C, what they are really saying is, let's supply it with an energy budget measured in multiple large nuclear explosions. And that's assuming perfect efficiency, which you never get in real systems. In reality, the engines or laser systems would waste huge amounts of energy as heat, scattering, and other losses. So the total required energy on the ground could be many times worse. Now compare this to Pluto-class missions. New Horizons went to Pluto with a cruise speed of around 14 to 16 kilometers per second. If you compute the kinetic energy for a 1-ton object at that speed, you still get a big number, but it's orders of magnitude lower than the energy at 10% light speed. That gap is exactly why chemical rockets, plus gravity assists, can just barely handle Pluto, but completely fail when you scale the problem to interstellar speeds. To get from 16 kilometers per second up to 30,000 kilometers per second, you're increasing speed by a factor of almost 2,000. Because energy depends on speed squared, the energy needed goes up by roughly 2,000 squared. That's about 4 million times more. So going from a Pluto-style fast probe to a Proxima-style relativistic probe is not just more fuel, it's millions of times more energy. This is why phrases like hundreds to thousands of times more are actually conservative. Even partial lightspeed missions crush you with energy demands. And we've been ignoring relativity so far, just to keep the picture simple. But once you start pushing to a significant fraction of light speed, the usual simple formula for kinetic energy starts to underestimate the truth. Relativity kicks in. As your speed gets closer to light speed, it effectively takes more and more energy to get each extra bit of speed. You never reach light speed, you just need an increasing amount of energy for smaller and smaller gains. The curve bends upward. That means our earlier estimate for 10% light speed with non-relativistic thinking is already a best-case simplification. As you push to 20%, 30%, 50% of light speed, the energy requirement climbs even steeper than the speed squared rule suggests. So every just a bit faster step toward reasonable travel times to Proxima multiplies your energy bill again. Put it in plain terms. The energy cost to make even a small 1-ton probe go fast enough for interstellar travel is not something you can hide inside a single launch or a single reactor. It's a civilization-scale amount of energy, equivalent to running a big fraction of the planet's entire power output for extended periods, and focusing that into one mission. Pluto missions, by comparison, sip from the global energy budget. We burn some chemical fuel, we use a bit of nuclear material in an RTG, we're not bending the whole civilization around a single probe. A Proxima mission at 10% light speed would be gulping energy instead of sipping. You'd need massive power plants, huge laser arrays, or enormous propulsion systems, and you'd have to keep them running at high output long enough to push that probe up to speed. Then you'd face a similar challenge if you ever wanted to slow down at the other end. It's like building a global industrial project just to throw one small object across space at insane velocity. So now stack everything you've heard. Insane distances, rockets limited by deep physics, mission times that dwarf human lifespans, hardware and software slowly destroyed by radiation and time, power sources that fade, navigation that demands near perfection, communication delays measured in years, human biology that cannot handle the trip, and an energy bill that looks like it belongs to a Type 2 civilization, not the one we have right now. At this point, you might be thinking, fine, then we just need a completely new kind of engine, something more advanced, nuclear, fusion, antimatter, or maybe something even more exotic, warp drives, wormholes, all the things you see in science fiction. If chemistry and solar panels can't do it, maybe those will. But here's the catch. On the hardware side, almost all of those ideas are still drawings and equations, not machines you can bolt to a spacecraft. By now, it's tempting to say, all right, chemistry is weak. Let's just jump to the cool stuff. Fusion drives, antimatter engines, warp bubbles, all the buzzwords you hear in sci-fi talks. If distances and energy bills are this bad, surely the answer is a new kind of engine, right? Something that makes Proxima hard but doable, instead of forget it. So let's go through them one by one and look at where they actually are. Not in slides, not in concept art, but in terms of hardware you can bolt to a spacecraft. First, nuclear thermal and nuclear electric. These are the near-future ideas you see in serious mission studies, not fantasy. Nuclear thermal rockets work by running a reactor as a super hot furnace. You pump liquid hydrogen through it, heat it up to a very high temperature, and blow it out the nozzle. That gets you exhaust speeds maybe 2 to 3 times better than chemical rockets. Instead of a few kilometers per second, you might reach around 8 to 9 kilometers per second. That's a big deal for missions inside the solar system. For Mars, it can cut travel time, give you more flexibility in trajectories, and let you carry more payload. For outer planet missions, it can mean faster transfers or bigger probes. Nuclear electric is a different flavor. You use a reactor to generate electrical power, then run ion engines or other electric thrusters. Those can throw propellant out the back at tens of kilometers per second, much higher exhaust speed than chemical, but with very low thrust. They push gently for a long time. Put these together and you get a clear picture. Nuclear thermal plus nuclear electric can make Pluto missions easier and more capable. You could fly heavier orbiters, you could get there faster, you could maneuver more at the target. They're great for better solar system exploration, but they don't come close to breaking the Proxima barrier in a practical way. Even 10 or 20 times better performance than chemical is nowhere near the thousands of times you need to hit a big fraction of light speed with a serious spacecraft. Next level up is fusion. This is the same process that powers the sun, fusing light nuclei like hydrogen into heavier ones and releasing huge amounts of energy. In principle, fusion rockets could heat and expel exhaust at tens of thousands of kilometers per second, which would give you the kind of exhaust speed you need for meaningful interstellar missions. That's why old studies like Project Daedalus imagined multi-stage fusion ships that could reach around 10% of light speed with big, complex vehicles. On paper, the physics is super attractive. High energy density, very fast exhaust, long burn times. But here's the blunt reality. We have not built a single fusion power plant on Earth that produces more energy than it consumes in a stable, continuous way. All of our fusion experiments are still in the research phase. They're huge, delicate machines that live in buildings, need teams of scientists, and run for short bursts, not years. So going from we can barely do experimental fusion power on the ground to we can build a compact, reliable, restartable fusion rocket engine that runs for years in vacuum without maintenance is a massive jump. We'd have to solve fusion power first, industrially, then shrink and harden that technology, then integrate it into a propulsion system. That is multiple major breakthroughs deep, and none of that exists as flight hardware today. Push further and you hit antimatter, the ultimate fuel on paper. When matter and antimatter meet, they annihilate and convert nearly all their mass into energy, according to the famous energy-mass relationship. That's about as efficient as you can get. A few kilograms of antimatter and matching normal matter could, in theory, power an insanely energetic rocket, perfect for starships. In practice, we produce antimatter in tiny quantities, nanograms per year in particle accelerators, at insane cost, and most of it is used up in experiments, not stored. Even if you had the budget to scale production up, you then have to keep that antimatter from touching any normal matter for years or decades. That means holding it in ultra-clean electromagnetic traps with perfect stability, because any containment failure is instant energy release, like a very small bomb going off inside your spacecraft. So when you hear antimatter engine, think fuel that is theoretically perfect, but practically unavailable and almost impossible to store safely at meaningful scales with current tech. It's a great topic for research papers and sci-fi, but it's not something we can even begin to deploy in an actual deep space mission yet. Then there are the really exotic ideas, warp drives and wormholes. These show up in the equations of general relativity as mathematical solutions. The Alcubierre drive is a theoretical model where you contract space in front of a ship and expand it behind. So the ship itself never moves faster than light locally, but the bubble of space-time moves it effectively faster than light relative to distant observers. Traversable wormholes are shortcuts through spacetime, connecting distant regions with a tunnel. They're fun to talk about and they're useful as thought experiments, but they come with requirements that are far beyond anything we've seen in nature. They seem to need exotic matter with negative energy density, or weird spacetime conditions that we have never observed or created. Not in particle accelerators, not in astrophysics, nowhere. So right now, these concepts are firmly theoretical. They are not engineering projects. Nobody is building a warp prototype in a lab. We're still at the stage of arguing about whether they're even physically possible once you consider quantum effects and real materials. So when you zoom out, what do you see? Nuclear thermal and nuclear electric are promising and likely to be used for advanced solar system missions. They can help us do Pluto and beyond more effectively. Fusion, antimatter, warp, and wormholes live much further down the road. Fusion and antimatter might be reachable with enough breakthroughs in physics, materials, and engineering. Warp-like ideas might turn out to be flatly impossible or so constrained that they're useless for real travel. But crucially, none of these advanced propulsion concepts, not even the near-term nuclear ones, currently exist as tested, scalable space hardware for interstellar work. We do not have a fusion rocket. We do not have an antimatter drive. We do not have a warp bubble generator. We barely have early-stage nuclear thermal test programs. For Pluto, you can walk into a clean room, see a chemical rocket stage, see a probe with an RTG, put them together and actually launch. For Proxima, everything that looks promising is still a design on paper or a simulation on a screen. That gap between cool concept and metal in space is exactly why Proxima stays in the not yet category. Not because the ideas are wrong, but because the hardware is missing. And even if you imagine we fix propulsion tomorrow, there's still the medium you have to travel through. Everyone calls interstellar space empty, but at the speeds you need for Proxima, that almost nothing starts to behave like a wall. So the next question is, what actually happens when you throw a starship through the thin gas and dust between the stars at a significant fraction of light speed? You keep hearing that interstellar space is empty, but that word is misleading. It tricks you into thinking there's nothing there to worry about. The truth is, once you go fast enough, even a thin haze of atoms starts to behave like a barrier. Between stars, the average density of gas is around 1 atom in each cubic centimeter, sometimes less, sometimes a bit more. Compared to Earth's atmosphere, which has around 10 to the power of 25 molecules in that same volume, that is an insanely good vacuum. So at first glance, you think, no problem, that's practically nothing. But remember what you're trying to do. You're not drifting slowly. You're talking about speeds like 10% of light, around 30,000 kilometers every second. When you slam into atoms at that speed, each individual atom carries a lot of energy relative to your ship. It's like driving through a fog of tiny bullets. Everyone is small, but their impact energy grows with the square of your speed. So at a fraction of light speed, that thin gas creates real drag and heating. As your starship plows through this medium, it will generate a kind of bow shock in front of it. The gas gets compressed and heated. Particles smash into the leading surfaces. That energy has to go somewhere. It becomes heat and radiation. You have to design your hull and shield so they can deal with that energy without melting, cracking, or slowly eroding away. That's not trivial when you're trying to keep mass low and systems stable for decades. Gas is only half the story. The more direct threat is dust. We don't know the exact number and size distribution of dust grains along any specific path to Proxima, but we know dust is there in the interstellar medium and in the outskirts of the solar system. At low speeds, these grains are just small particles. At 10% of light speed, they turn into serious weapons. Imagine a dust grain with mass around a milligram. That's too small for your eye to notice on Earth, but at 0.1 times light speed, the energy it carries when it hits your ship is comparable to a hand grenade going off. That's enough to punch through thin shielding, damage instruments, and throw fragments into your structure. And you can't guarantee that you only hit one grain. Over long distances, you're sampling a lot of space, so you must assume multiple impacts. To cope with that, your starship or probe would need serious shielding on its nose and leading edges. One idea is sacrificial shields, sometimes called debris or Whipple shields. You put a thin outer layer that shatters incoming particles and spreads the impact energy before it reaches the main structure. You might layer multiple shells, or even send empty sacrificial plates ahead of the main craft, knowing they'll slowly be ground down over time. But that means your shielding is being eaten away, not just tested. Every impact removes a bit of material, heats it, cracks it. Over millions or billions of kilometers, those tiny hits add up. Even at more modest deep space speeds, tens or hundreds of kilometers per second, a craft that travels for thousands of years sweeps through an enormous volume of space, plenty of opportunities for small collisions. Surfaces get pitted, sensors get slowly sandblasted, optical instruments like telescopes and cameras lose clarity. Radiators can be damaged, antennas get small dents that change their performance. Instruments you carefully calibrate on Earth can be degraded to the point of being nearly useless by the time you reach your destination. And the longer you fly, the more of this cumulative damage you have to assume. Engineers have proposed more advanced shielding methods. Some involve using magnetic fields, others use plasma. The idea is to create a protective bubble around the ship that deflects charged particles before they hit the hull. A powerful magnetic field can bend the path of ions and electrons, and the plasma cloud can help spread out the impact zone. Conceptually, this can reduce the load on physical armor and lower erosion rates. There are even ideas to use this interacting field as a kind of brake or sail, a magnetic sail that pushes against the interstellar medium, letting you slow down without expending propellant. But all of these concepts are at the simulation and theory stage, not at the "we flew this for decades at high speed" stage. We have never flown a long-duration mission through the true interstellar medium at significant fractions of light speed to see how these systems behave in practice. And none of these field-based shields fully solve the dust problem. Magnetic fields mainly act on charged particles. Many dust grains are neutral or only weakly charged. They'll still slam into your hull. So you probably need both, physical shielding for dust and field shielding for particles, adding complexity, mass, and new failure modes to a ship that already has to be extremely reliable. Now compare Pluto and Proxima in terms of environment. For a Pluto mission, most of your path is inside the heliosphere. That's the bubble of space dominated by the sun's wind and magnetic field. The sun pushes back the interstellar medium out to a boundary called the heliopause. Inside that boundary, the particle environment is different. More solar wind, less direct interstellar exposure, and we actually have some data from missions like Voyager and New Horizons about what that region is like. By the time you're going interstellar, you've punched through that boundary, and you're living in the true interstellar medium almost the entire way. Different gas pressures, different magnetic fields, different radiation environment, and much more uncertainty. We don't have detailed maps of dust density all the way to Proxima. We only have models and indirect measurements. So every assumption about how thick to make your shields or how strong to make your magnetic bubble has to include wide safety margins, which again means more mass and more cost. For Pluto, the medium problem is serious but bounded. It's one more thing you design around for a decade-long mission through a region of space we've already probed. For Proxima, the medium itself becomes a major risk factor. You're moving faster for much longer through an environment you don't fully understand, and that multiplies the uncertainty in your mission design by orders of magnitude. So now, stack that on top of everything else: the distances, speed limits, time, power, navigation, communication, biology, economy, energy, and now an almost empty space that behaves like a slow grinder on your hull when you push fast enough. You're not just fighting one big obstacle, you're fighting a whole network of them that all interact. At this point, a very basic question comes up. Even if you could somehow brute force through all this, is it actually the smartest way to do science right now? Or are we trying to build a ridiculous tool for a job we can almost do from home? Look at Pluto first, because it shows you what worth it looks like on a realistic timescale. When New Horizons got there in 2015, we went from a blurry pixel to a real world. You suddenly saw mountains of water ice, some rising a few kilometers high, nitrogen ice glaciers flowing across the surface, giant plains that looked geologically young, and hints that there might be a subsurface ocean hidden under all that frozen nitrogen and methane. One flyby rewrote textbooks. It changed Pluto from cold, dead rock at the edge to complex, active dwarf planet. And that happened inside a time window you can actually plan around. From early proposal to data return, you're talking roughly 20 to 25 years. That's a long haul, but it's still one scientific career. People who helped design the mission got to see the images, analyze them, and publish the results. The data rate was low, but it was enough. We got detailed maps, compositional information, atmospheric profiles, and then more data from the Kuiper Belt object Arrokoth later on. A single mission delivered a massive, immediate science payoff, and it did it with technology we could build and launch in the early 2000s. Now, compare that with what you realistically get from a Proxima flyby. Be honest about it. If you somehow managed to launch a probe that could reach, say, 10% of light speed and survive the journey, when it arrived at Proxima System, it would be moving so fast that a full encounter with any planet there would last hours or less. There would be no chance to break into orbit, no drones, no landers, just one high-speed pass. At that speed, the data pipeline would be brutal. Limited onboard power, limited antenna size, a gigantic distance to Earth, so the data volume would be tiny compared to what we're used to. Maybe a handful of images, a few spectra of an exoplanet's atmosphere, a few measurements of the star's environment, and then the probe would be gone, flying deeper into the galaxy, out of range or out of power. And now layer time on top of that. Travel time is still decades at best, maybe centuries if you're not hitting extreme speeds, so the people who authorize, design, and build the mission will never see that handful of images. The scientists who proposed it will be long dead. The data, if it arrives at all, will be for a completely different generation, maybe a completely different civilization, and you've accepted insane technical risk and cost for a tiny, delayed dataset with no follow-up. Meanwhile, what else can you do with the same kind of money and effort? This is where the competition kicks in. Large ground-based telescopes like the Extremely Large Telescope with a 39-meter primary mirror and future space observatories can study exoplanets from right here in the solar system. They use high-resolution spectroscopy and clever imaging techniques to separate the light of a planet from its star. With that, you can already measure atmospheric compositions, look for molecules like water vapor, oxygen, methane, carbon dioxide, and check for combinations that might be biosignatures, hints of life, all without sending a single kilogram of hardware out of Earth orbit. Those projects cost billions, not trillions, and they deliver science within 1 or 2 decades, not 1 or 2 centuries. On top of that, big telescopes can look at hundreds or thousands of targets, not just one. You're not betting everything on one star system, you're spreading your risk and your payoff. You get to compare many worlds, not pray that the one you picked for your interstellar shot actually has something interesting and that your probe survives long enough to see it. Then think about risk in a hard, strategic way. If a Pluto mission fails, you lose a decade of work and hundreds of millions of dollars. It hurts, it's a serious setback, but it doesn't break your civilization. You learn, you improve, you try again. You can propose another mission within a generation and your space program keeps moving. An interstellar mission is different. If you commit centuries of planning, trillions of dollars of infrastructure, decades of industrial buildup, and then the mission fails halfway, maybe from a software bug, a navigation mistake, an impact with dust, or a power system collapse, you don't just lose a spacecraft, you lose a huge fraction of your long-term effort. Your grand project becomes a ghost, a story about how you spent hundreds of years building something that never reported back. Rational planners, scientists, and governments look at that and hesitate, not because they lack imagination, but because it's a terrible risk profile. Extremely high cost, extremely long timescale, extremely low ability to intervene if something goes wrong, and no guarantee that the science return will justify all of it, especially when other cheaper methods are improving every decade. So the strategic reality right now is simple. As long as we can learn almost as much science with big telescopes, solar system probes, and near-space infrastructure, as long as we can scan exoplanet atmospheres from here, study protoplanetary disks, map galaxies, measure gravitational waves, and explore icy moons and asteroids without leaving our own star's backyard, a Proxima mission is a bad bet for funding. Great for inspiration, terrible for budgets. That doesn't mean never, it just means not yet. But this not yet is another reason Proxima is effectively impossible today. It's blocked not just by physics and engineering, but by priorities. We can unlock a lot of the universe from here, right now, for far less money and far less risk. So interstellar flight stays a dream, sitting behind a whole queue of projects that are easier, cheaper, and already give us huge scientific returns. And that brings you to the last piece of the story, maybe the most important one for how you frame all of this. Saying impossible for now is not the same as saying impossible forever. Pluto itself used to be completely out of reach, and now it's in our photo albums. So the real question is, what has to change at the level of technology and civilization before Pluto is epic, Proxima is impossible, flips into Pluto is routine, Proxima is hard but on the table? So after all of this, here's the real question you're left with. Did we just prove that Proxima is off limits forever? Or did we just prove that you're early, that you live in the wrong kind of civilization for that kind of mission? Start with Pluto, because Pluto tells you something very important about what you can already do today with all your limitations. Your species has already taken a probe roughly the size and mass of a piano, launched it off Earth, sent it more than 5 billion kilometers away, over 3 billion miles, and hit a moving target smaller than the moon, after 9.5 years of flight with the arrival timing nailed down to within minutes. That is not a casual achievement. That is extremely precise navigation, long-term planning, rock-solid engineering, and mission control that stayed focused for more than a decade, with a spacecraft that had to work almost perfectly the first time. You had one shot at the flyby, and you pulled it off. That's what barely possible looks like, and it proves that outer solar system missions, as extreme as they feel, are inside human reach. Now put Pluto next to Proxima and see what Proxima forces you to admit. When people say, why don't we just go to the nearest star? This is the checklist you have to run. Distance, propulsion, time, power, navigation, communication, radiation, dust, human biology, psychology, economy, industrial capacity, and raw energy. Any one of those on its own would already stretch our current tech, push our budgets, and force new engineering. But for Proxima, you don't get to handle them one at a time. You multiply them. You stack all of them together and you ask, can we handle this as a single system with no major weak link over decades or centuries? The honest answer right now is no. You're not one magic engine away from a Proxima mission. You're dozens of breakthroughs away across completely different fields, all of which have to line up and then stay stable for a very long time. So if Proxima is not yet, what does yet actually look like? What is the likely path from here to there? It doesn't start with a starship. It starts with upgrading what you can already do in your own backyard. Before anyone seriously builds an interstellar probe, you will probably see routine missions to the outer planets and the Kuiper Belt. Not once-in-a-generation shots, but regular orbiters around things like Neptune, Uranus, maybe even Pluto itself. Missions that stay and map and sample for years, not hours. You'll see advanced nuclear or high-efficiency electric propulsion flown on solar system missions, not just in papers but in actual hardware. Nuclear thermal stages sending cargo to Mars quickly. Nuclear electric tugboats moving heavy payloads between orbits. Ion or plasma drives with much higher exhaust speeds than today, tested over decades around Jupiter, Saturn, or beyond. These are the proving grounds for anything you'd later trust on a Proxima probe. You'll see massive space infrastructure start to appear. Large power stations in orbit or on the moon. Factories that can build big structures in space instead of lifting everything from the ground. Huge telescopes in solar orbit or on the lunar far side, doing exoplanet science that we can only dream about right now. And as all of that comes online, you'll also see better AI and robotics, systems that can run complex operations autonomously for years, then decades, without a human hitting buttons every day. In other words, before you touch Proxima, you'll probably behave like a civilization that truly lives in its own solar system, not just visits it sometimes with probes. You'll be mining asteroids, building habitats off-world, running large power grids in space, and treating the outer planets as normal destinations, not exotic adventures. That leads to the bigger step, the civilization-level milestones. There's a rough way of thinking about this called the Kardashev scale. It sorts civilizations by how much energy they can command. Type 1 uses the full power available on its home planet. Type 2 uses the power of its star. Type 3 uses the power of a whole galaxy. You are not a Type 1 yet. You don't fully control the energy flows on Earth. Your total power usage is only a tiny fraction of what hits the planet from the sun every second. Interstellar flight, especially at a decent fraction of light speed, is really a Type 2 problem. You're talking about energy levels and infrastructure where tapping a noticeable percentage of your star's power output becomes normal. Once humanity can routinely generate and move terawatts in space, not just on the ground, once you're running large nuclear or fusion plants off-world, once you can launch or assemble thousands of tons of hardware every year, not a few thousand tons total from all rockets combined, then the equation changes. At that point, building a gigawatt-class laser array for beamed sails or a fleet of heavy fusion tugs or a massive shielded interstellar probe starts to look like a big project, but not an impossible one. Mission timelines of 100 or 200 years would still be long, but you'd have space-based industries and autonomous systems that have already proven they can run for that long. You'd have outer solar system missions with century-level continuity in your rearview mirror. So the honest conclusion, the one you should say out loud in your video, is this. Right now, reaching Pluto is the hard edge of what we can physically and financially do with fast flyby probes. It's the barely possible outer limit of our current spaceflight. And even then, we only did it once with a small spacecraft and a lot of luck and precision. Reaching Proxima Centauri, even with a tiny uncrewed probe, demands speed, power, robustness, navigation, autonomy, and sheer energy on scales that make Pluto look like a short road trip. Nothing in physics says you can never do this. There's no cosmic law that bans us from going. What's stopping us is everything about our present technology, our present economy, and our present biology. Together, they all say the same thing: not yet. And that's the real twist. You don't live in a galaxy that's closed off forever. You live in the prequel, in the early era where Pluto is a once-in-a-lifetime headline and Proxima is still out of reach. You are at the stage where your species is just learning how big the problem really is and building the first tools to chip away at it. The line "going to Proxima is impossible" is true for you now, but it's also an invitation. It's a line some future civilization might look back at and deliberately rewrite. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.